Okay, let's get started. Welcome, everybody. It's a pleasure to have Andrea Bajcsy join us today. Andrea and I first met in algorithmic HRI. The first time her advisor, Anka, was teaching it. And Andrea was top of the class. She was answering all the questions. She was doing great. I slept in every single class. And so she's one of the world's best HRI researchers. I've never done a human study. And so that's where we're at. But Andrea has done some of the most exciting work in learning, in control, in safety, and in human-robot interaction. And she's won all the awards. I can't even list them. But she's currently at CMU. And yeah, please take it away. It's your time.
Thank you so much, Abhishek. It's lovely to be here. I always have a really good time whenever I come to UW. So let's just dive right into it. Okay, every day I open up Twitter. I start scrolling through these videos that look really impressive of what is broadly colloquially termed a generalist robot. And these are typically powered by some sort of a very exciting foundation model. And for all intents and purposes for today's talk, what we're gonna use to mean like generalist robot is one robot that can do many things. So the same robot could clean up a machine shop, repair a bike, put your dishes away, fold paper to make origami, make you a fruit snack, et cetera, et cetera, et cetera. You'll notice though, these are all from different companies, but in theory, one robot could do many things. And I think this is actually very exciting. Like, I hope we succeed. I genuinely do. What I'm curious about is what happens after we get some notion of a generalist system. Specifically, what I'm really curious about is what does it mean to safely deploy a system that can literally do anything? And a lot of the times, when we talk about what safety means in robotics, for a long time this has meant something like, okay, I want to make sure I avoid collisions. Maybe I want to have some kind of compliant control with the environment. But when you talk about a generalist system that can do anything, safety hazards are significantly more nuanced and complex than collision avoidance. This is just a small series of examples of hazards that can happen. Spilling, tearing, breaking, mixing hazardous chemicals, breaking items like this. The list goes on and on. And so the question that I'm kind of curious about is how can we generalize what it means to make a safe decision in this era of a generalist robot? And the hypothesis I'm going to be putting forward today, and the actual foundational research question I'm personally very curious about, is I believe that a nuanced safety behavior can only emerge from an equally nuanced representation of the world. And we're going to dive into this hypothesis through a series of concrete research problems that we've been kind of investigating. Just to put you in the right headspace, the way I think about what safety means, it's technically inspired by a very broad, deep literature in safe control. When I talk about safe control, I think for me it's more like a guiding light. It's a way of thinking about, of representing sequential decision-making problems which underlie everything that we do in robotics. I am not necessarily referring to a prescriptive set of tools. Okay, it's more of like a way to represent or model the problem. And then what we're going to be doing is that we're going to be drawing upon all of modern generative AI as the way by which we construct interesting representations of the world and also computational models that let us scale a lot of these paradigms that we kind of know and love. And so today I'm going to walk you through some three bodies of work that have been going on in my lab, and if we have time, I'll end also on some kind of maybe some philosophical notes. But first, we need to all agree. Yeah, what is it?
When you say safety, what does that mean? Are you going to talk about it?
He's a plant. Okay. Yeah, we gotta agree on this because, man, the number of times at a conference I hear someone give me a vibes-based definition of safety, it's killing me, okay? And, people use all these terms, they're like failure and safety and blah, blah, blah. Reliability, robustness, these terms all get thrown around. So I'm gonna be very precise about what I mean to begin with, but it's important to recognize that there are many ways to define this. So this is how I define it. And the way we're going to learn about what safe control is through a very old idea, this idea of something called a safety filter. Basically, the idea is I'm going to give you a very complex autonomy stack, maybe it's an end-to-end policy, maybe it's a human teleoperator, maybe it's multiple modules stitched together. I don't really know what it is, but what I want to do is I want to wrap this system around with this thing called a safety filter, which what it's going to do is it's going to monitor the generations from this model, and it's going to correct them so that the current decision you are taking are not causing future hazards. And to understand this, let's talk about how to construct a filter. I'm going to call this cooking it up. Okay, so there's 4 ingredients that you typically need for safety. We're going to use this running example because it's really, really pedagogical of this little ground vehicle. It's going to be moving around this environment. And the first thing we need in our cookbook is we need a state space. For a simple system like this ground vehicle, it's going to be really easy to write down. X, Y position, velocity, things like this. I need to know what's going to happen next as a result of my decision. This is what a dynamics model is. I can either have an ODE, I can have a discrete time system, I can even make a call to a high fidelity simulator. In robust control, which is an important category of safe control, what we typically do is we also think about uncertainty through the perspective of robustness. We say there's something I can't model about the world. It's oftentimes called an opponent or a disturbance. It lives in some finite set of things that could ever possibly happen. And it's going to help me model things that I don't really know but could disturb me. So it could be another adversary that messes with me. It could be hard to model aspects of the environment like friction or external forces applied to my system. And last but not least, we got to specify, what does it mean to fail? Okay, failure typically, when we talk about it, means a subset of your state space, which is bad. So it's a constraint satisfaction problem, essentially. There are important other kinds of safety, like alignment. I'm happy to talk about that later as well. But here, we're going to talk about constraint satisfaction. Okay, these are the ingredients. Let's now cook up a safety filter. So here's just a top-down projection, assuming I know where all the obstacles are and I know exactly what I'm trying to avoid. There are many ways to talk about the construction of a safety filter. The specific tooling I'm going to talk about today is something called Hamilton-Jacobi reachability. It is not important for all of you to become experts on this. It is a deep, rigorous, complicated mathematical topic. I'm going to give you intuition for what this does. Okay, the idea is I'm going to convert this constraint satisfaction problem into an optimization problem that's going to let me use lots and lots of nice numerical tools. And the way I'm going to convert the constraint satisfaction problem into optimal control is through encoding the failure set as the sub-zero level set of a function. Specifically, this is typically a sign distance function. It tells me how close I am to failure. If I give you this, what I now want to figure out is for any initial condition of my system, okay, I want to figure out, does there exist a sequence of actions my robot can take so it steer clears of this failure set? And this should be true despite this worst case perturbation induced by the opponent, by the adversary. Okay, formally this ends up looking like this kind of safety critical dynamic game. It is not, again, important for you to understand all these details. Let's talk about the intuition of what the optimal value of this game means. Intuitively, it basically says, tell me the closest my system ever got to failing, despite the robot's best effort to prevent failure and the disturbance's best case strategy for causing failure. There are many, many ways to solve this game. It is not easy to solve. It's actually a very active area of research. Today we have tools like grid-based PDE solvers, adversarial RL, self-supervised learning. More new ones are coming out every day. Next time you see your favorite applied mathematician, say thank you to them. They're working very hard on this. But let me show you the result of one of these computations working in practice. Okay, so you see this value function being computed. It's turning red as we're doing the computations. Let's play it one more time because it's so cute. Okay, so we're running a solver. We're computing this value function. What does it mean? What does it mean? The value function, and actually also the optimal policy, give us some nice things. So the first thing it gives us is we can extract from this the optimal safety preserving policy, which for any state the robot is in, it tells me what is the way for me to avoid failure the most. So for this really toy example, it's pretty intuitive. Okay, so anytime I'm close to the obstacle, I try to turn very far away from it, right? This is Dubin's car system. The boundary, this red boundary, sorry, it's a little hard to see, but this boundary we just computed, which is the sub-zero level set of the value function, This actually is what sometimes people call the safe set. Maybe it can be used as a runtime monitor. There are many ways to refer to it, control invariant set. But the idea is that the interior of this red set is a set of all states from if I start, I can stay away from failure for all time. If I leave that set, there's nothing I can do. I'm doomed to fail. And so what we typically do when we design a filter is we design some scheme for shielding some nominal policy. For example, if you're on the interior of that set, do whatever you want, run your favorite policy. If you're on the boundary of the set, this is the point of no return, you must execute the safety policy. There are much smarter ways of doing safety filtering. You can look at these really nice related survey papers here for more details, and I'll touch on one very briefly at the midpoint of the talk. Okay, you are all now control theory experts. Let's see this in practice. Now, one of the problems with this formalization is that you don't typically know the failure set a priori in a lot of robotics problems. For example, in this autonomous ground vehicle example, you don't know where all the obstacles are a priori. You're building them, for example, through some kind of mapping algorithm. And so some of my old papers here was, okay, how can we recompute the safety filter online based on new sensor data we get? You can see that safety filter being updated in the upper right-hand corner. You see that boundary is going to be changing. Whenever the base policy, this is an end-to-end vision-based policy, gets a little optimistic, it tries to cut through the interior of the obstacles. The safety filter takes over control, and it steers it away. And so these two policies play back and forth like this, and we're updating them in real time. This is some older work. Okay, what's the problem? The problem is that under the hood, the majority of safety representations are all collision avoidance. Here is some of my old work. For example, collisions between two agents. This is also some of my older work, collisions between the robot and the environment. For a lot of humanoids, right, the worry is the humanoid falling onto the ground, right, collisions with the environment. There's a lot more work here, of course, but that's typically what we mean when we say safety. But how do I represent these kinds of safety problems? I want my robot to interact with the environment, but I don't want it to cause these harmful outcomes like spilling, tearing, breaking. And this is where we're going to take our first step along the set of works that I promised to show you. So what is holding us back? What is so hard? Let's go back to our ingredients. And we're going to use a running example throughout this section of the talk, where we have this robotic manipulator, and it's interacting with this open bag of candies. I know, candies are not actually that safety critical, but it is pretty annoying to clean up a bunch of candy spills in my lab. Okay, so we are worried about the following scenario. If my robot messes up, it might pick up the wrong bag of the Skittles, pull up really hard, all the contents of the bags are spilled. So the first question I would like all of you to do in your mind is ask yourself, what is the state space of this problem? Does anyone want to guess? What is state? What do I need in my state space?
Pose of every single Skittle, as well as the appearance of the Skittle bag.
Yes.
Some form of deformable object model, infinite dimensional, and many things that I'm missing.
Yeah.
So it's large.
Yeah, probably something also about the robot itself. When I gave this talk in the RI, one of the senior faculty was like, do you need the color of the Skittle? Is that really important?
Definitely.
And probably, right? I like the red ones way better than the yellow ones. And so I don't care if you spill the yellow ones, but those red ones, you gotta preserve them. Okay. Also, yeah, to Sid's point, right? Representing the deformable bag is really hard, right? A lot of times the guesses I get is okay, let's do a mesh. That's a really nice representation. But there are many other things you could do as well. Okay, even if I wrote down a state space, I concatenated all these components together, what is dynamics? How do I forward simulate what's going to happen next? Super, super hard, right? And then even if I had this, the specification of what it means to be in failure is super hard, especially because for the majority of the time, I can't observe the property that I really care about. It's really, really hard to know if the Skittles are, where are they in the bag? How close are they to actually hitting the table?
Can I ask a
Please.
question here? I wanted to ask this before, but maybe this might be a good example. There's two aspects of the dynamics, at least when I've thought about safety for self-driving. One is partial observability, which is true here with the Skittles. You don't know what the Skittles are and how they're moving. And the other one is just stochasticity of the forward model, right? I'm sure having known this field, I know that we'll address this in the future, but can you forewarn the audience on that? Yeah.
Actually, some of my philosophical discussions at the end precisely touch on this. I think, are you familiar with like Laplace's demon? So Laplace's demon is this idea, like Laplace was haunted by the idea that if you write a sufficiently rich representation of the world, the full world becomes like deterministic. Yeah, and he's like, what if that's true? So I too am haunted by this demon. Let us hold that conversation for the end. I think it's a really, really good question. That ventures into philosophy. Okay, so although we do not know how to write down state or failure by hand, we can make an assumption. Let us make the following assumption. Failure is observable from high-dimensional observations. So if I show you this image, you can tell me, yep, you failed. The problem, of course, is I need to be able to predict if my decision is going to cause this. Because by the time I've seen it, it's too late. So don't give me just a classifier which is always running and telling is there Skittles, that's too late. And so the idea that we're going to explore here is, since it's so hard to write down all these models, let's instead rely, again, on the power of generative modeling to construct a state space, essentially through training with a bunch of high-dimensional data, learning to compress this, learning to transition it. And then we're going to do all of our safety computations within this learned state space representation. Yes?
You mentioned 4 components for safety.
Yeah.
The 4th thing was disturbance. So
Very sharp, very sharp. I'm intentionally hiding that for 1 second until the end when we get to the philosophy. And if you just wait for a few months, we'll have a nice answer. But yes, very sharp. For now, let us assume disturbances do not exist as we are going into this representation of the world. Very good, very sharp. Everyone's paying attention. They're going to get a good grade. Okay, so before we had this, now we have this. It looks aesthetically very simple. In practice, it is not necessarily as simple. Right? Before, we had to write down all these states, and like our safety specification was like a very complicated collision checker. Our dynamics was one of these models. Now, our state space is going to be some encoding of, ideally it needs to be a history of images. Our safety specification is going to be a classifier in this version of the work, which is just going to look at the latent state and tell me, are you spilled or not? And then our dynamics are going to be a world model. Please.
You can also say, ask questions at the end, Sid.
If they're fast.
Yeah. I guess like one challenge with having dynamics in the embedding space is that like the properties that you have in, like Lipschitz or like whatever it might be are no longer necessarily true, right?
Yep.
And I guess like the theorems that we need to prove in this space demand that we have some assumptions about the ensuing dynamics.
Yeah, the discrete time reachability stuff we'll talk about, it technically only needs bounded dynamics, but not Lipschitz.
But
and
still,
these are bounded. It's a neural network, right? So we bound the output of it.
But the embedding, I guess you have to ensure that the embedding is actually, I mean, if you use like ResNet or some other like standard embedding, right? Like those are meant for semantics, not necessarily for like any form of continuity.
Yeah, we can have a longer discussion about this. It's really hard to understand these latent spaces and what structure you need to impose to get a good one. We have some ongoing work on inspecting them to know if they're sufficient or not. But let's hold that off because honestly, it's like a fundamental research question that I'm very curious about in general. Okay, let's talk about what is a world model so we're on the same page. I don't mean like a unconditioned video generation model. I specifically mean one that you can condition with actions. The way you train it is you get lots and lots of diverse observation action pairs. This is in fact complementary to behavior cloning, right? Because every time you do something weird and wonky that you don't want to regress, you just throw it into this model. And then there are many designs to world models, but generally it looks something like this. You learn to compress your high D observations into some latent state Z. You then learn a transition function given the latent state and your current action into some next latent state. And then, oftentimes in your data set, you know exactly what happens next. And so now you can train this via many different objectives like reconstruction, teacher forcing, et cetera, et cetera. And in the specific works you're going to see today, we built this on some like recurrent state space model work from older, like Dreamer v3 style models. And also we play with the Dino world model that came out more recently when we go to hardware. Okay, safety specification, what is it? I show you the images, I get you to label them. Are they in failure or not? So remember, this isn't if I am doomed to fail. It is, have I already failed or not? So I look at them and I say, okay, anytime there's Skittles, you're bad. And then what I do is I can train a classifier on this. It's going to look at the latent embeddings, and it's going to learn to essentially discriminate, does this latent look like it is in failure or not? And so again, anytime the classifier returns to you, for example, a negative value, it means that you're inside of the failure set, but now the failure set operates inside of our latent embedding space rather than in the physical space. To be very clear, this is not a proper dense sign distance function. This is a classifier. And in fact, the fact that you don't have a proper like metric space is actually kind of bad for some of the optimizations, and we could talk more about those details later as well, but for now, let's just worry about the classifier. Okay, what is our latent safety problem? We've removed the disturbance, so it's not a minimax game anymore, but we still have this min over time because we want to figure out the closest we ever get to failure. We have a subset of our latent states, all of which if I took a embedding from and I decoded, this is a real decoding, I would see spills. And then starting from any initial observation, my mission is to figure out, okay, is there anything I can do to stay away from this spilling? Right, so in other words, we're trying to figure out, given the best effort to avoid failure, how close does the robot come to failing? And if I ran this computation, in this case, we're going to solve, instead of just forward simulation, which is not very efficient, we're going to solve it kind of dynamic programming style. Specifically, we use reinforcement learning inside the latent space. But this is essentially the dynamic programming backup for this min over time optimization. It looks kind of familiar to the expectation version that you guys might have seen before, but you just have to keep track of the closest you've ever gotten with this outer min.
And this is happening offline, right?
Correct.
Like
this is all
a bunch of
pre-computed.
data, right? Okay.
Exactly.
Okay.
Yep. Yep.
I get it.
Absolutely. Okay. So if I ran the computation and I asked the value function which latent states are assigned a positive or negative value, you would discover something like this, which is actually quite cool because, for example, one thing you might discover is a scenario like this is in the unsafe set. You have, if you were teleported to this universe where the bag has already been pulled up so high, no matter what you do, physics is going to do its thing, stuff is coming out the bag. But you automatically discover this through just the optimization.
I guess the worry here is that there are so many things in the Skittles that can go wrong that you might be overestimating. You might be too scared, right? This is a problem with min-max control anyway, because there may be one very super subtle move that you need to do with the Skittles that needs to get you out of there, but that might not be in your data density data set because it's and I don't know if you observed that.
Yeah, there's a lot of problems. There's problems where if your world model has not seen enough coverage of actions and observations, then you can't discover the right actions to overcome. In practice, we actually find our optimization to be overly optimistic rather than pessimistic. So we have done some post hoc calibration, like statistical calibration, to make sure that it works. I can comment offline on why it is optimistic. It's a function of the world model, essentially. Yes?
You're looking for unsafe things under any policy, under your nominal policy?
Good question. This is under any policy. So does there exist any policy, in your policy class, which is your neural network representation, that can...
Okay, but
it's basically solving the dual problem, actually, right? It's trying to find one way out of there, right? That's a dual problem.
And there's some things that are important to take care of when you're trying to shield a nominal policy with this, which I'll comment on a little bit later. Okay, ultimately you get two ingredients out. The monitor, the policy. Here's how it works at deployment time. So exactly like Sid mentioned, you pre-compute it, and then at deployment time you carry around these two mathematical objects. You query them at every single latent state by embedding your observations. You're checking, oh, am I safe or unsafe? I'm good. And you get too close to the boundary. At some point you say, ooh, I'm pretty sure if I continued I would be doomed, so let me instead run my least restrictive safety control law here. So let's see this in hardware. This is the setup you've seen before. We all know and love it. We have two cameras. One you can't see. It's a third-person camera. One is a wrist camera. And here I'm going to show you safeguarding a human teleoperator, mostly because I surely don't know what's going on in a human's brain. So there's no way I'm going to do a policy optimization with them. But that's because, because our optimization doesn't care what the base policy is, for any base policy, we know if we're doomed, we're going to be able to deploy our safety filter this way too. And if we don't safeguard the human teleoperator, it's very trivial for them to interact with the bag inappropriately, and that's what we want to safeguard them from. For world model training in these experiments, we use 1,300 rollouts on the robot. The majority of them were actually collected randomly. My student just sampled from a Gaussian or whatever and had the robot essentially do play with the environment. 10% of those are explicit unsafe demonstrations we collected, and 10% are explicit safe demonstrations. Then I pre-compute this offline, and then it's time to deploy. So let's see what happens. The thing to pay attention to here is this is what the robot sees at deployment time. The filter runs 15 hertz or less, depending on the engineering tricks you play. And anytime the border around these images turns green, it means that the robot is correcting the teleoperator. If there's no green border, it means that the human is autonomous. Okay, so the first thing is the human decides to go try to grab the top of the Skittles bag. There's no green border. They're fully in control. Life is good. The next thing the person's going to do is they're going to grab the bottom of the Skittles bag and start to shake side by side. So the filter actually allows them to shake side by side, but if you look at the optimal safety-preserving action, it doesn't stop them. It actually slows them down, which makes sense. You don't have to stop shaking, just don't shake so fast. Finally, if you grab the bottom of the bag and you try to pull up really hard, that command is completely canceled out because that is surely unsafe. In hardware, we trained the world model with the dyno encoder. So we follow dyno world model. We made no innovations on the world model itself. And in fact, because the dyno encoder is so robust to like visual features, we find that like for small perturbations in the Skittle bag colors, the safety filter still works. So we bought all the flavors of Skittles we could. These are all OOD. We only trained on classic Skittles. But it turns out the dyno encoder and the representation is still pretty good, which makes sense. This is exactly what dyno was trained for. Recently, we also had a really fun time deploying our latent safety filter for the opening of the new Robotics Innovation Center. We ran it for over 2 hours with people from the Pittsburgh community. These were non-experts, just playing around with the robot, trying to get it to spill the Skittles, trying to be protected. It is not 100%. You know, we had 3 people who found really creative ways to spill the Skittles that were certainly out of distribution.
Hire them.
No, exactly, for data collect, yeah. But it was still really cool to see this just deployed in the wild and helping the majority of people. This like lane assist for home robots is what we're calling it. You don't have to just safeguard humans. You can also safeguard autonomous base policies. So for example, here, if you have a diffusion policy that for some reason does the wrong thing, what you can actually do is with some clever design of the safety filter, you can actually remove unsafe modes from this base policy. So maybe this base diffusion policy, for some weird reason, does this wrong behavior. If you do the least restrictive safety filter I just showed you, where we're just switching, you'll surely keep the system safe, but you're actually going to harm performance, right? So the robot can't actually pick up the bag at all. But if you get smart about the way you do filtering, here this is optimization-based filtering, so essentially think of it as any action that's proposed by the base diffusion policy. Dimensions of the action space that would be unsafe are projected away. If you do this, then you can actually guide the base policy towards safer grasps. And now back to Abhishek, your point, to do this you have to be kind of careful with the way you train the model. And essentially the way we do it is we have to get rollouts both from the base policy you're shielding as well as the safety controller so you have coverage of the alternatives in the queue function. Okay, I want to show you when things don't work because this is very exciting as well. Okay, one way it doesn't work is you take the Skittles bag and you rotate it 180 degrees. The opening is not visible to the end effector's camera nor to the third person camera. And so of course the safety filter says, yeah, it's fine, let's just let you do that. And so you fail.
Do you have a decoder on the generative model? Like, can you tell what it was hallucinating?
Yeah, so for the Dreamer world model, you'd co-train it with an encoder and a decoder. For Dyno, you technically don't have the decoder. You can train it and look at it. Yep. So all the visuals you see are from this extra decoder we train. Yeah.
I'm just wondering, like in this case of like being OOD, like what is it hallucinating?
So this, yeah, I guess I don't have exactly that result for you now.
Cool. No,
Yeah. Okay, another failure is I have a deep appreciation for the difference between different candies dynamics. I used to think M&Ms are the same as Skittles. They're not. Skittles bags are they're very waxy, while M&M bags are super papery and thin. Peanut M&Ms are heavier than Skittles. Okay, so our model is trained super narrowly. It doesn't generalize. This is not surprising. It's just machine learning. Okay, but exciting future work. So next up, we've been actually alluding to this problem a little bit, which is this notion of OODness, right? And so the motivating example here is the following. Think about Jenga. How many of you have played Jenga before? Raise your hand. How many of you think are really good at Jenga? No one thinks they're good at Jenga? Well, my robot isn't that good at it either. Okay, so why is Jenga hard? Jenga is really hard because there's too many outcomes that you've probably never seen, right? Like, you probably don't have coverage of every single way you can ever pull the block and like see what's gonna happen next. And fundamentally, it's really, really, really hard to safeguard something that you can't predict. So here's an example of some world model hallucinations that happen precisely because of this problem that you're asking the model to predict outcomes of actions it's never seen. So on the top, you see the actual data that the robot sees. On the bottom, you see the imaginations. They're short horizon imaginations. And you see it's oftentimes really optimistic. Like the robot, when it picks up the cube or the block, it thinks that the items will stay on top, and they certainly do not. And the specific action has never been seen in the data set. So if we go back to our problem, this is the true failure set. By the way, I'm drawing it as this like nice, contiguous, like it's not. Okay, it's like these weird blobs all over, but just it's easier to visualize this way. Your world model is trained on some portion, some coverage of the full space. You have some known failures that you've seen before in your data and you've labeled. But the problem is that sometimes you might be in a state and then you query the outcomes of a particular action sequence, and it could take you to a potentially totally benign state, or it could take you into a portion of your failure states that you've never seen before. And so one of the things that we did in this work was we said, what if we look actually at the world model's epistemic uncertainties? This is uncertainty kind of from data coverage. And we use the world model's epistemic uncertainty as a proxy for unseen failures. This is surely overly conservative, but it's still a step forward. Specifically, the way we do this is we train an ensemble of world models. This is not possible in general, but it was possible for this particular class of models that we were looking at. And what we do is we calibrate the disagreement amongst the ensembles via a statistical technique called conformal prediction so that we get essentially an in-distribution recall guarantee. I can't guarantee anything about OOD because I don't have labels by definition, but I can at least tell you that with high probability, I know that this is something I've seen before. Okay, so now my safety specification, like that failure set F, is now the union of out-of-distribution states and known failure states. And if I do my safety filter computation, essentially what I'm doing is I'm now trying to stay in distribution and away from known failures. And just to show you an example of this in hardware with the Jenga game, so here we're shielding a teleoperator again. On the left, you're going to see the original latent safety filter. On the right, you're going to see our uncertainty-aware one. It's called UniSafe. And I want you to pay attention here. You're going to see the robot resist. So do you see how it's going like, So this is the safety controller being like, I do not know what is going to happen next. And it actually causes the teleoperator to change their strategy with interacting with the cubes, and it goes upwards. Yeah?
So I guess often in offline model-based RL, you're already conservative because you try not to exploit the model. Is it the same thing? Like, because, I mean, you're doing dynamic programming there, you're doing dynamic programming here, you're adding like some variance penalty or something. Like,
yeah, actually we have a bunch of baselines related to...
And the difference is the conformal prediction, or like what gives you gain over just like offline model-based RL?
Yeah, I think there's probably a few ingredients. We can take a look at the paper to show you kind of the different axis of variations that we tried. I think the conformal prediction is very helpful for just figuring out that right boundary versus just heuristically trying to figure it out. There's also certain differences that emerge in terms of the optimization when you're doing this min over time versus expectation. So there's a few confounds this way.
Okay.
But we did compare against like some popular offline model-based RL approaches, yeah. Okay. Any other questions also from the students? Yes.
So, like here's one place where we are saying we want to avoid out of distribution because it can be unsafe. And there's like the flip problem of exploration and online RL.
I know.
Where you want to go OOD.
I know.
Like,
yeah.
How do we? They seem like two sides of the same coin.
Yeah.
How should we think about that?
Yeah, I mean, the safe learning community has been like plagued by this for a long time, right? How do you safely explore? I don't know. To be totally frank with you, I don't have anything super smart and deep to say about it, other than I agree with you. It is a hard problem, and it's hard to know when it is worth taking that risk or not. And so I don't have anything deep to say yet, beyond the fact that I agree with you, and I would like to think about it more deeply. Yeah.
Perhaps you'll touch on this, but I suppose all of these methods require you to have a set of data in which you have failed or reached some unsafe state, which is okay in these examples because that's just like you've spilled your bag of Skittles or you've knocked over your tower. But in the real world, this would be like you've mixed two chemicals and created mustard gas, or you've like left something flammable on the radiator and you've created a house fire. It's like you'd never actually ever, even in a training set, want to reach these states. So how do you manage these unsafe examples where you'd really never even ever want to reach?
I'm actually also very plagued by this too. I believe that quote unquote bad data like this is actually very important. I have a position paper if any of you want to read. It's called Good Embodied Reward Models Need Bad Behavior Data. It was recently accepted to ICML as a spotlight talk, so you can also check it out there. So I believe in the need for the bad behavior data. I agree with you though, where do you get it? One of the reasons why actually generative models are kind of exciting is because you could imagine with advances, like the advances we've seen in image painting imply that I could maybe do nice data augmentation where I can like ask Gemini to, in-paint images of fire in my static scenes. So maybe I could do the same thing and I could in-paint an entire like temporal sequence of a hazardous event. I don't know how, generative models also themselves are not necessarily, perfect and magical either. It's a frontier technology, but that could be one way to get around it, is the ability to generate these hypotheticals without having to actually experience them. But it's very hard, very hard. Okay, let us move on. And by the way, I'm showing you guys a lot of like qualitative results. We have lots and lots of experiments in these papers. I just want to focus today more on intuition building, on understanding what the algorithms and the problems are. But please check out all these papers for the nitty-gritty ablations and studies and all these kinds of things that my students did. Okay, let's keep moving on. Let's talk about inference time policy steering. Okay, the context in which we're going to talk about this is specifically that as you start looking at these more instruction environments, what a safe behavior even means is super, super context dependent. So for example, crushing a chip bag really firmly is totally fine if I want to make a crunchy topping. It's bad if I want to preserve the integrity of the chip to eat it as a snack. And so the question that we asked here was, okay, what is the role of essentially knowledge in these pre-trained foundation models to enable this context-dependent detection and prevention of failures? And so here's the setup. We have some tasks that the robot is doing for the user. Serve a cup of water to the guest. The robot has some base imitation-based policy. In this case, it's a diffusion policy. And it learns lots of different strategies for how you can interact with this cup, right? And the way that you can express these is by taking samples from the model and rolling them out on the robot. The problem, though, is that not all samples from the model result in the same task performance. So for example, there might be samples that grab the cup by the handle. That's pretty good for serving someone. There might be scenarios where I grab it by the lip. That's pretty bad. That's contaminating the cup. There might be samples where I knock it over, et cetera, et cetera, et cetera. So not all samples from the action model are created equal. The thing, though, is that the base policy, it actually might already contain the correct behavior mode inside the distribution. What we need to really do is verify that the robot sampled action plan are actually leading to the outcomes I want. And the actions alone don't tell me this, right? So what we can do is we can think of this as essentially a model predictive control problem, where instead of just optimizing over my continuous action space, I'm optimizing over a set of samples I take from the model. So maybe here I have 3 samples for the sake of pedagogy. And what I need to now do is I need to somehow predict what is going to happen, what is the outcome of taking an action. And then I need to also verify if this outcome is the right outcome for this particular context. Of course, the math is very nice. How do we actually do this tractably is the question. And again, we're going to follow a similar key idea. Let's use, again, the latent representations learned by a world model. But now let's actually align a foundation model, in this case specifically a vision language model, to directly reason about the latent states for evaluation. Here's how it works. We take the setting. So here we have our observations. We encode them. For each action sample, we forward predict the outcomes. These are the latent space trajectories. If I decoded them, here are real decodings of these samples. So you see the different outcomes happening. I want to be very clear, though, in this work, we actually don't use the decoded imaginations. We do all of our reasoning in the latent space. I understand the desire to want to decode because it's a nice interface to the foundation model. The foundation model is trained on images. But actually, you're asking the foundation model to do the hard state estimation again. You just did this in the world model. So technically, I think it makes a lot more sense to keep everything in the latent because I've already done the hard state estimation problem for you. Yes?
Do I need latent? Can I just have a safety queue function? Like, does it matter? Like something that, it's a thing that takes in Z and outputs like likelihood of failure or something. Like, do I need to forecast latent states in the future? Like,
oh, I mean, in theory, I mean, you could use, for example, the safety queue function we saw from before and just do a one-step prediction. Yeah.
you can just do that.
In theory, you could. There's pros and cons for why you may or may not want to do that. Yeah, we can talk a little bit more offline. OK, so I've predicted outcomes. I'm going to keep everything in the latent space. And now what we do is we play the following trick. We say, if I really want to tap in to the common sense, context-aware understanding that is inside of all these vision language models, what is a vision language model? It's just an LLM, right? LLM backbone with a little bit of extra image data. And so ideally what I should do is I should somehow translate all of this nice embodied representation of the world in Z into a textual representation, because then I can really tap into everything the model is good at. So what we actually do is we decode all of these latents into a textual narration of what is happening by fine-tuning a VLM to essentially be, think of it like video captioning, but in the latent space. And so what you get is, so here's a little prompt, right? You ask the LLM, OK, the robot is trying to grab the cup from the table. Please provide a sentence that best describes the robot's behavior, and you pass in all the latent tokens. Then you get these narrations. The robot attempts to grab the cup by the handle. It seizes the cup through the interior, blah, blah, blah. The robot fails to achieve a secure grasp. So you get all these descriptions of what has happened. And now you can just call the model again, and you can be like, OK, well, here's the context. The context is I'm serving a cup to a guest. Which one is most appropriate? And the model says, oh, OK, I think mode 1 is the best one because it's appropriate, doesn't contaminate. So you can think of essentially the VLM is also doing the argmax as well. So here's an example of that cup task. Again, cup picking up is not actually like the hardest task in robotics right now. I think it's just a nice pedagogical example for the algorithm. This is a training time environment here. Serve the cup of water to the guest. But if you change the context, 0 shot, the model can work. So this is a new task description we never gave the model. But we just said, oh, the handle is covered in oil. And it will avoid the handle. Here's a chip bag example. Avoid crushing the contents inside versus maximize stability. You'll see the policy steering algorithm select this like super stable grasp versus this more delicate grasp. There's many problems still with this pipeline. One of them that was on our mind was that actually VLM verifiers, while powerful, are very overconfident. This is a known problem even in just like normal LLM land, let alone an embodiment. Here's an example of some of the kinds of problems you might see. So now we have this peg insertion task. Same exact architecture. We have a base policy, it's diffusion. We have, we translate all the action samples into textual outcomes, and we have the reward model. And here the task is to put the purple peg in the hole on the table. And here are just some examples of the narrations you might get from sampling a few times from the base policy. Put the peg on the left, on the right, the peg drops. You can also add the none of the above option, and you can have the VLM reason about this. And it turns out, for this particular base policy, it's only trained to put pegs on the left or the right holes on the table. The problem, of course, is that I didn't really specify which one I want. And so what happens here is the VLM basically flips a coin. And it's like, OK, I'm just gonna pick left. Sorry, I'm going to pick maybe right. But the actual person maybe wanted the left. I just forgot to specify that in my original instruction to you. Another problem that can happen is maybe I perfectly specify everything I care about. Align the purple peg with the top left hole inserted. By the way, this is how we have to talk to robots now because a lot of the language is very limited. OK, so I say all these nice, precise things. The problem, though, is when I take samples from the model, actually this model is kind of imprecise. So it turns out all of the samples I took are doomed to fail. It's just really, really an imprecise policy. But again, the VLM is just going to, it's not guaranteed to pick none of the above. It oftentimes is biased to pick one of these. For example, just saying try left but fail, the try sometimes causes the model to place lots of probability mass on that. And the model will say, let's try it out. OK, and then it fails. So what we thought about was, well, okay, could we somehow calibrate the verifier to distinguish the difference between kind of semantic ambiguity in the task versus low-level action feasibility of the policy, like none of the samples are good, and then select an appropriate resolution strategy. If you're confident, execute the right one. If you have semantic ambiguity, clarify. If you have low-level action feasibility problems, then you should retrain. And let me show you kind of how the pipeline works in the same exact example from before. This paper was just accepted to RSS, so it's hot off the press. So now this model is calibrated. I am not telling you the details of how we do this calibration. I'm happy to talk about this offline. I just want to build intuition for what the system can now do. So in the ambiguous scenario, what happens now is essentially we run a conformal prediction style procedure. Conformal prediction is going to give you a set of options. It's going to return to you a set such that the true label is included in that set with high probability. And so in this case, it actually returns a set with two entries in it, left and right. And as soon as you have a set like this, you say, oh, okay, let me try to synthesize a query to ask you, okay, do you want the left or the right hole? And the person says, oh, I wanted the left one. Okay, great, then I'll execute that corresponding action sample. On the right-hand side, when you're incapable and when you're imprecise, what happens is the calibration procedure returns to us a singleton, but the singleton is just the none of the above option. So whenever I return to you none of the above, this means I should probably initiate some kind of fine-tuning or retraining process with the human. So in this case, I say, oh, I can't, can you please teach me? Then you start some kind of interactive imitation learning kind of process, and then maybe you redeploy your policy, and now you have improved it. So in this case, we train, for example, a residual policy on top of the base model to get the model to be a little bit more precise. And across, we did a few tasks here, like nut and peg from RoboMimic, table cleanup, peg insertion. And essentially, the key takeaway here is that other ways of kind of soliciting feedback that look at maybe low-level action uncertainty in the base model, like Ensemble Dagger, or just hope that the human intervenes whenever, they lead to lower quality learning data compared to our method, which is disentangling low-level skill capability versus high-level task uncertainty. Okay, with this, we have done our deep dive. Now I want to just get a little bit philosophical, and then we're going to wrap up. So let's end by taking a step back, and I want us to recall that dirty laundry slide, right, that I showed you earlier. There were two things that I mentioned in the dirty laundry slide. One was some question about observability, and there was another broad question about dynamics, right, about the ability to predict futures. So the first thought exercise I want all of us to do together relates to observability. Okay, is it safe to serve this milk to someone for breakfast? Okay, so I don't know if you can read it, but the expiration date is 18th of October 2026, so probably not expired. The color doesn't look weird. When I pour it, it doesn't pour chunkily. That's Gemini's fault. That's not on me. Thank you very much for catching that in future versions.
I thought that was the whole point of the slide.
That's what I get for making slides late at night. Thank you, Abhishek. Okay, pretend it's 2026 on the right-hand side as well. Okay, if I'm a robot is making decisions based on these visual cues that I'm paying attention to, my decision will be life is good, I should serve the milk. Okay, how do you and I check if it's safe to serve the milk? I gotta smell it. Okay, the spoiled state is literally unobservable without smell. I think our robots should smell and taste and touch, and I think they should be hurt as well. I think they should need to feel all these things for the record. I think it's very fun to think about that. Okay, so what does this imply to us technically, right? There's a question which is kind of on my mind, which is, okay, what is the role of multimodality when you learn a state representation, when you're going from just lots and lots of high-dimensional signals into some meaningful unit of the world? What is that? How do you do that? Let's talk about dynamics. Some people theorize we all have world models inside of us. Let us all use our world models to predict what might happen if I tilt the bag upwards a little bit. We're all doing the forward simulation a little bit. Okay, there's many possible outcomes. Okay, maybe lots of the contents in the bag come spilling out. Maybe none of it comes out. There are many, many possible outcomes. And this actually goes back to the connection about robustness, that disturbance, which is, what is the role of maybe robust optimization when we think about stochasticity intrinsic inside of world modeling? If we believe that the world model is good at capturing lots of diverse outcomes, how do we actually leverage this? And so I want to basically just close by saying, stay tuned. We're working on some initial answers to these questions. So please stay tuned and check out our lab website for some early results related to both of these questions. All right, with that, I want to say thank you to all my amazing students. I want to say thank you to the sponsors who support us. And with that, I'm happy to take any of your questions.
Question.
I know the students have questions because I've been meeting with lots of you guys. You better ask me hard questions. Yeah.
Yeah, so I noticed in one slide you had like a picture of the sim, but a lot of them had like real life like images of the robot. Have you noticed any differences like deploying like policies in sim versus the real world, or? Yeah.
Like in general, like
Yeah,
like
like
policies in sim versus real.
Oh no, like with your like safety like observability, have you like noticed any differences between like transferring sim to real or anything like that?
We actually, so my lab has not been doing lots of sim to real right now. Anytime we do it, it's just real.
Okay.
So, no, I guess.
They behave differently in sim than they do in real. Like the sim look different than real. Right? Like is the.
I see. I guess the nice thing about sim is like your ability to just get data coverage. So like life is really good in simulator because you just churn the data crank infinitely. And so a lot of the problems that might plague us in real are a little bit easier to tackle in sim. Of course, also the visual features of simulation are also kind of easier. My students, we recently moved labs. We used to be in the basement. We moved labs because the students said it's so dark. We would like to be not in the basement. I said, yes, let's move you up, up the ground. But now the students are like, oh, but like every time the lighting changes from the day to the night, my algorithms don't work as well. Okay, so now we're struggling with these kinds of problems, which of course you never struggle with in simulation. So there are some of these common problems, but yeah, that's kind of where we're at. Yeah.
So latent space station lets you go beyond collision avoidance, but you have to have human labelers. Mm-hmm. Are you overly reliant on this classifier? And is there any way to get around this classifier that's used in like, your work?
Well, how would you like to remove the classifier?
I don't know, but like you can only be as good as your classifier, right? Like basically, and it's hard to have this classifier generalized. I feel like that's like, yeah, I don't know if you have thoughts about that.
I have a slight follow-up.
Okay.
Are you more sensitive to false positives or false negatives in that classifier?
Oh, that's a good question.
But yeah, please.
No, we have an extensive study about this. I'm trying to remember what the trends were. In low-dimensional settings, because you can get really perfect data coverage, we get really nice like classification accuracy in general. In hardware, off the cuff, I think we're more sensitive to false negatives. Negatives being, I think I am safe, but I am not. Because the world models are optimistic right now, and we're not doing robust optimization. But I can check with my students to get you exact numbers. Other questions? Yes?
So back to the coffee example at the end where like, the amount you tilt the bag up, it can change. Since you have this like line of work doing this latent aligned VLM stuff, and you can kind of encode what's happening in the past as text, like is there some kind of way to reduce uncertainty through the latent aligned VLM plus like describing what has been happening without having to train a model that can ingest a ton of states as like historical context for world modeling prediction?
Let me try to refine your question. Are you asking how to like information gather in the world model?
I guess it's like when you're doing something that has high uncertainty, like what you are doing helps resolve that uncertainty as you're trying to perform the task. But
yes. Yeah, so actually, so if I understand your question correctly, so some of the work that we're going to push out in the next month or so is trying to take a baby step towards this. Basically, I would like to select a decision which minimizes the probability, for example, of bad events happening, right? Or maybe I want to make the distribution as peaky as possible around the right mode that I want. And so you can control, to some degree, some of the stochasticity within the models through the choice of the action. Yeah, or stochasticity in the outcome, as modeled by the model. Yeah, I don't think I answered your question about the failure classifier. I need to think a little bit more about it. I mean, I think I'm trying to understand what is the underlying thing you're looking for in your question. Basically, one way to interpret your question could be, could you learn the safety behavior directly, maybe, instead of having to learn the classifier and then doing the computation? Is that one way of interpreting your question?
Sure, yeah.
Sure, okay.
I feel like maybe it's overly reliant on the classifier. I don't know how to get around it. I'm just wondering if you have thoughts about it.
Yeah, I have no problem with the classifier, so maybe that's why I'm struggling to answer your question. In the sense that I think like you need to know what is good or bad.
Yeah, you have to know.
Like how else do you make a good decision? The question I think for me becomes more, how do you get a good classifier rather than how do I remove the classifier? So for example, what do I mean by good? I would like a dense classifier, one that gives me real valued signals for how close I am to failure versus just the boundary. How do I do that without having per frame labels that I could never get? Right, so that it's very similar to reward learning, right? It's the same kind of problem. Yeah.
Well, the quick thing is like if I know that car crashes are bad, but no one classified car crashes for me. Right? Like I didn't have to see a bunch of pictures of car crashes to know that they're bad. So like maybe you can get away. You know the concept of what is bad even without experiencing.
Yeah, or for example, how can you learn to generalize from like toy versions of badness into real versions of badness? Like you know how like children learn with like blunt scissors what it means to cut something before you actually cut something that's very worrisome. Yeah, how do you do that concept abstraction? I think that's a really, really cool question. Yeah.
I guess just following up on that, you showed some examples earlier where I guess just like the naive safety strategy of just rolling out the safety policy is maybe overly conservative because it just stops. And presumably that's at least partially because the failure set is specified with just the classifier. Like if you had a more something like design distance function, but in limited spaces, maybe you wouldn't necessarily have to do some like optimization-based stuff to get more sophisticated recovery behavior.
100%. In fact, there were two ingredients we had to do to get. Oops. There were two things we had to do to get this nice behavior. One, which is what I mentioned to Abhishek, we had to get smart about how we optimize the Q value with this mixture of data from the base policy we're going to shield, as well as the safety policy. And the other innovation we had to do is to play around with the way that the classifier is kind of shaped. So the classifier, we got kind of this like pseudo smoothing of the classifier to give us nice, denser margin signals. It's just a proxy, but it worked empirically pretty well. So the better you can do that, the better the overall pipeline will be.
Okay, I think we are at time. So yeah, let's thank Andrea again. Thanks for coming.